So in this video we're going to be looking at some examples of metrics, and I've just written out the different metrics which we're going to be looking at in case you want to skip through the video and find the example you want. The Euclidean metric, the discrete metric, the max metric, and the taxicab metric. And obviously there are many more, but we're just going to look at these four in these examples. And I've also reminded us of the three conditions we need to prove for these things to show that they are in fact metrics. So the distance between any 2 points is 0 if and only if they're the same point. The symmetry property that the distance from x to y is equal to the distance from y to x, and the triangle inequality, which is always the hardest to prove. These two are generally easy to prove for every example. So let's start with the Euclidean metric. So example 1 is the Euclidean metric. Euclidean metric. This should be very familiar since we were looking at it last video for the two-dimensional plane, but we're just going to go ahead and straight away generalize this for n-dimensional space. So this metric takes 2 points in n-dimensional real space and gives us a real number, which is our distance. And what it does is it takes point x and a point y, say these are both points in n-dimensional space, and maps them to the sum of the squares of the difference between each component. This is just normal geometry. This function should be pretty familiar. So let's just go back and look at the conditions which we want to satisfy. The first one, that the distance between any 2 points is 0 if they're the same point, and that 2 points are the same point if the distance between them is 0, and also the symmetry property that if you just interchange the position of the variables, then it's the same distance. So the first one is obviously quite obviously true. If this distance is equal to 0, then these must be the same point, because these are all positive numbers, so they must be 0 if the whole thing is 0. And if these are the same point, then obviously this is 0, because you'll just be summing a bunch of zeros here. And the symmetry property is also very obvious if we just interchange the components of x and y in this summation, just swapping these around. So this is like d of yx is equal to yi minus xi squared, which these two are obviously equal, right? So now all that's left to prove for this is the triangle inequality. But to do this, we're going to have to prove another inequality first. This is called the Cauchy inequality. So I'm just going to find some space to do this. So this is just an inequality which we're going to use to prove the triangle inequality, and this takes this form. It's a bit might look a bit overwhelming, but it's relatively straightforward. That the square of the sum of the products of the components of 2 points in n-dimensional space is less than the product of the sum of the squares of each component. And this is called Cauchy's inequality. Inequality. And the way you prove this is, let's consider the function f of t equal to the sum from I equals 1 to n of ai. So a and b are points in n-dimensional space. So this is the sum of some ai plus tbi, and notice that this is ai plus tbi squared. So this function we're considering, and let's notice that this is greater than or equal to 0, right? This is a sum of squares, so it's always greater than or equal to 0, and it's also a polynomial, a quadratic equation in terms of t. So if we just expand this out here, we get that this is equal to t squared times the sum. I'm just going to forego this I equals 1 to n. T squared times the sum of bi squared plus t times the sum of ai bi plus the sum of AI squared. Sorry, it should be a 2 here. So notice that this is a quadratic equation in T, but it's also greater than 0. And what do we know about quadratic equations that are strictly greater than or equal to 0? Well, they can't have 2 real roots. This has at most one real root because it only touches 0 once. So, well, what does this mean? Well, if it only has one real root, then its discriminant, this b squared minus 4ac, then this can't be positive. This is less than or equal to 0. So what does this mean? Well, if we just take if we just figure out what this is, then this is 4, the coefficient of t, this b squared. This is 4 times the sum of ai bi squared minus 4ac, which is 4 times the sum of ai squared times the sum of bi squared. And this whole thing is less than or equal to 0. And so we're done. If we just if we remove this factor of 4 and then just add this term to the other side, then we get that we get the original inequality. So this is proved. I hope that's pretty straightforward, the step from this thing to this thing. So let's just go back to our Euclidean metric and try and prove the triangle inequality. So we already proved these first two axioms of the metric in the Euclidean metric. So we're now going to prove the triangle inequality using Cauchy's inequality. So let's take a look at the triangle inequality. This d of xy plus d of yz is greater than or equal to d of xz. And so this is what we want to prove. So to prove this, what we're going to do is we're going to take the square of all these of both sides, because these things are non-negative terms, right? So if this square is greater than this square, then the original inequality will hold, because we know that none of these things are negative terms. So let's prove this. This is a lot easier to prove, and we can use Cauchy's inequality to do this. So we're just going to start evaluating this expression here, which is just move down a little. So d of x y plus d of y z squared. We're going to just evaluate this. So this is equal to the root by our definition of the sum of xi minus yi squared plus sum of yi minus zi squared. And so if we just expand these brackets, I have to write very small here. I'll just do the algebra. Xi was this is root squared, so we have one of these, and again on the other side. Squared plus 2 times a big root of the sum of xi minus yi squared zi squared. Okay, but notice that this, if we just take this to be a single number, this xi minus yi, that this is here we can apply Cauchy's inequality, right? Because we have the product of a sum of squares of some components, and this is greater than or equal to, if we just take a quick look at it again. So this is, so our xi minus yi takes the place of our ai here, and our yi minus zi takes the place of our bi here. So this is greater than the product of greater than the square of the sum of the product of the terms. So what are the terms? The terms are xi minus yi and yi minus zi. So so this term here is greater than or equal to 2 times the root of the sum of xi minus yi minus zi squared, which is just because this is now the root of a square. This is greater than or equal to 2 times the sum of xi minus yi minus zi. And so now we can just take the sum out of factorize the sum out of this expression essentially. So we have now that go back to my original color, that our original expression d of xy plus d of yz squared is greater than or equal to the sum of xi minus yi squared plus zi squared plus 2 xi minus yi times yi minus zi. And so this we can now factorize, and we know how to factorize this. This is just equal to the sum of xi minus yi plus yi minus zi squared. And so these cancel, and we're just left with the sum of xi minus zi squared, which is equal to d of xz squared. So we have finally that this expression squared is greater than this distance squared, and so this proves our triangle inequality. This took a little bit longer than I planned, so the next video I'll do the other 3 examples of the max metric, the discrete metric, and the taxicab metric.